This is Lab 3 Circuits. The purpose of this lab is to explore time-dependent voltage and current in an RC circuit. We're going to play around with the circuits to predict the behavior of circuits containing resistors. We'll use ammeters to measure current and potential differences, as well as voltmeters, and we'll examine the behavior of ohmic resistors and capacitors. We'll apply principles of energy conservation, which is the loop rule, current and charge conservation, which is applied through Kirchhoff's current rule, aka the node rule, and the definition of steady state in our circuit exploration. So this procedure for our simple circuit was that we were going to explore charge and energy conservation with just a simple circuit containing two 1.5 volt batteries, two resistors, two ammeters, and we will adjust this simple circuit to create a graph demonstrating charge and energy conservation and to calculate resistance of circuit elements. So here you can see the two ammeters, the two resistors, and the two batteries all connected by a wire. So results from this simple circuit experiment, we predicted the values of the current of the ammeters to be 0.20 amps, calculated using the equation delta V equals IR, and the actual values were shown to be 0.20 amps. Our predictions were correct. We also played around with the circuit to reverse the ammeters, flipped them upside down, and the voltage reading was the same. This doesn't change when a voltmeter is attached because current flow doesn't change when a voltmeter is attached. Because the voltmeter simply reads potential change between 2 points. If we replace the ammeter with a voltmeter, as shown in the picture to the right, the voltmeter read a voltage of change of -3 volts, and the ammeter current reading decreased to 0 amps. In this setup, the voltmeter disrupted the flow of current, so the voltmeter showed the loss of all electric potential of the circuit, and the ammeter confirms that the current stopped flowing with this reading of 0 amps. So here are results from the simple circuit calculation where we determined the voltage change through different resistors. So from points C to D in this circuit, through resistor 1, the potential decreased by 0.96 volts, and then across the second resistor with a higher ohmic resistance, the potential decreased more, which is to be expected with a higher resistance, decreased by 2.04 volts. As shown in this potential versus position around the circuit graph. Then using the potential difference measurements, delta V from potential versus position graph in the slide above, and current measurements from the ammeters, the resistance R of circuit elements were calculated to be 48 ohms and 102 ohms for the two resistors, which is very close to what they actually were. So it's just a decimal error, not enough significant figures to have the same value. And then the wire and ammeter were both shown to have resistance values of 0 ohms because there was no voltage change through the wires and through the ammeter. So this is the procedure for the second circuit, the RC circuit, which was constructed to include a 10 or 20 ohm bulb, one 9-volt battery, and a 200 millifaraday capacitor. The elements were connected with wires to charge the capacitor, and the battery was removed from the circuit, and the wires were reconnected to discharge the capacitor. And here's a video of what that looked like. So the wires were connected, the capacitor started charging up, current started flowing, and the light bulb lit up, but then began to dim out. So what happens when the wires connect all the circuit elements? The bulb lights up and then fades out. This is because current flows in and through the capacitor, accumulating charge until the Imax is reached and the current stops flowing, causing the light to fade out. What happens when the battery is removed and the circuit is reconnected? This was not shown in the video, but the bulb also lights up and fades out because current flows out and through the charged capacitor until charges dissipate and the potential reaches 0. We also compared a 10 ohm bulb and a 20 ohm bulb. And the 20 ohm bulb has a higher resistance and was shown to take longer to charge and discharge, as shown in these experimental data down here. Then our final part of our experiment was a time-dependent voltage calculation across a discharging capacitor. So to the right, you can see the calculation of how we apply charge conservation, potential conservation, and then substitute in values of equations that we know, such as delta V equals Q divided by C, to get an equation that gives us the value for RC. Then we're able to plot this data as shown in the math above. plotting the natural log of change in potential over the initial change in potential, which is our y value, versus the x value time, giving us our slope that includes our RC value. We're given a linear plot, and then here in our plot, the slope was determined to be negative 0.166. And so from this slope calculation, we were able to calculate the time constant to be 6.002. And then just going off of our materials that we know we used in the simulator, a 30 ohm bulb and a 0.2 Faraday capacitor, the RC is calculated to be 6. So our math works out and we got the right value for our RC value. Some assumptions made in this experiment were that the ammeters in the simulation had no resistance and the wires had no resistance. And then also that charge flows instantaneously, that there's no like moment for the charge to start flowing, that everything is quick and seamless. Potential errors just result from the idealized simulator, which does not account for some additional resistance due to the real circuit components, such as wires and ammeters that actually do contain a small amount of resistance. What if we were doing this in a real life lab, and we use an actual ammeter instead of an ideal simulated ammeter? A real ammeter has some amount of resistance, as I just mentioned, while a simulated ammeter does not. If a real ammeter had been used instead of the idealized simulator ammeter, some electric potential would have been lost through the ammeter. The measurements of current on the ammeters would have been slightly lower in a real lab due to this additional resistance. And secondly, what if you were doing this lab in real life and you used a real battery to charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this happen in real life? If we set up the capacitor in this way, the capacitor would charge instantly because there's no resistance. However, a real wire does have a small element of resistance, so the battery would just charge the capacitor very quickly, not instantaneously. Our ideal model with a 9-volt battery predicts the capacitor to reach full charge in 25 seconds when a light bulb is attached. This would take a little bit longer due to some resistance in the wires connecting the elements if we were doing this setup in a real lab with a real light bulb and a real capacitor and wires. And that's all. Thank you.